Hello everyone, my name is Nguyễn Trung Hiếu. I'm from Group 3. Today our presentation is about access control list. So we will find out what is an ACL, also known as access control list. An ACL is a series of iOS commands that are used to filter packets based on information found in the packet header. By default, a router does not have any ACLs configured. However, when an ACL is applied to an interface, the router performs the additional task of evaluating on network packets as they pass through the interface to determine if the packet can be forwarded. An ACL uses a sequential of list of permit or deny statements known as access control entails. When network traffic passes through an interface configured with an ACL, the router compares the information within the packet against each ACE in the sequential order to determine if the packet matches one of the ACEs. So here is the several tasks performed of router require use of ACL to identify traffic. The table lists some of the tasks with examples based on a corporate policy. That's here the table of example. The next one is packet filtering. Packet filtering controls access to a network by analyzing the incoming and or outgoing packets and forwarding them or discarding them based on given criteria. Packet filtering can occur at layer 3 or layer 4. Cisco routers support two types of ACLs. Standard ACLs only filter at layer 3 using a source. The source are IPv4 address only. And the second one, the extended ACL or ACL filter at layer 3 using a source and or destination IPv4 address. They can also filter at layer 4 using TCP, UDP ports, and optional protocol type information for finer control. We will move to the next part in number and name ACLs. Number ACLs, the ACLs number 1 to 99 or 100, 1300 to 1999 are standard ACLs. ACL number 100 to 199 or 2000 to 2699 are extended ACL as shown in the output. This is the output. Number and name ACL. Name ACL is a preferred method to use when configuring ACLs specifically standard and extended ACL can be named to provide information about the purpose of the ACL. The IP access list global configuration command is used to create a name ACL. The rules to follow for name ACLs assign a name to identify the purpose of the ACL. Names can contain alphanumeric characters. Names cannot contain space or punctuation. It is suggested that the name be written in the capital letters. Entires can be added or deleted within the ACL. The next one is ACL operation. ACL defines the set of rules that give added control for packets that enter inbound interface, packets that relay through the router, and packets that access outbound interfaces of the router. The ACLs can be configured to apply to inbound traffic and outbound traffic. Inbound ACL Its filters packet before they are routed to the outbound interface is efficient because it saves the overhead of routing lookups if the packet is discarded. If the packet is permitted by the ACL, it is then processed for routing, best used to filter packets when the network attached to an inbound interface is the only source of packets that need to be examined. About ACL is filter packets after being routed, regardless of inbound interface. Incoming packets are routed to the outbound interface and processed through the outbound ACL. Best used when the same filter can be applied to packets coming from multiple inbound interfaces before exiting the named outbound interface. When an ACL is applied to an interface, it follows the basic operating procedure. Operational step used to traffic has entered router interface with an inbound standard IPv4 ACL configure are. One is the router extract the source IPv4 address from the packet header. 2. The router starts at the top of the ACL and compares to the source IPv4 address to each ACE in a sequential order. 3. When a match is made, the router carries out the instruction either permitting or denying packet and remaining ACEs in the ACL if any are not analyzed. 4. If the source IPv4 address does not match any ACEs in the ACL, the packet is discarded because there is an implicit deny ACE automatically applied to all ACLs. The last ACE statement of an ACL is always an implicit deny that blocks all traffic, and it is automatically implied that at the end of the ACL, even though it's hidden or not displayed in the configuration. The next one is wildcard masking. So, wildcard masking overview. An IPv4 ACE uses 32-bit wildcard mask to determine which bits of address to examine from a match. Wildcard masks are also used by the open shortest path first, also known as OSPF routing protocol. A wildcard mask is like a subnet mask in that it uses the AND in process to identify which bits in an IPv4 address to match. However, they differ in the way match binary 1 second and 0 second, unlike a subnet mask in which binary 1 is equal to match and binary 0 is not a match. In a wildcard mask, the reverse is true. The wildcard mask uses the following rules to match binary 1 second and 0 second. Wildcard mask match bit 0 match the corresponding bit value in the address. Wildcard mask bit 1 ignore the corresponding bit value in the address. So here the table lists of some example of wildcard masks and that what they could identify. The wildcard mask type. ACL 10 listen ACE that only permits host 192.168.1.1 0 equal a match and 1 equal ignore. To match a specific host IPv4 address, the wildcard mask 000 is required, resulting ACE in ACL 10 would be access list 10 permit 192.168.1.1 and 000. ACL 10 listen AC that permit all hosts in the 192.168.1.0/24 network. The wildcard mask 000255 stipulates that the very first 3 octets must match exactly the not the 4 octet resulting AC in ACL10 would be accesslist 10 permit 192.168.1.0.000.255. ACL10 is an ACE that permits on host in the 192.168.16.0/24 and 192.168.17.0/24 and etc to 192.168.31.0/24 network. The wildcard mask 0015 255 would correctly filter that range of addresses. The highlighted wildcard must be identified which bit of the IPv4 address must match. The resulting AC in ACL10 would be access list 10 permit 192.168.16.000.15.255. And here is the example of the wildcard mask calculation, as you can see on the slide. So the next one is wildcard mask keywords. Cisco always provided two keywords to identify the most common uses of wildcard masking. Host is substituted the 000 mask. This mask says that on IPv4 address bits match to the filter just one host address. Any it substitutes the 255 mask. This mask says to ignore the entire IPv4 address or to accept any addresses. In the example, the ACL10 ACE permits only the 192.168.10.10 host and the ACL11 AC permits on host. The keyword host and any could have been used to replace the highlighted output, accomplishing the name such as previous commands. So I will leave the next back to my partner.
My name is Quang and now is my presentation. Configure ACLs. Create an ACL or ACL must be planned, especially true of ACL requiring multiple ACEs. When configuring a complex ACL, this is subjected to use a text editor and write out the specifics of the policy to be implemented. Add the iOS configuration command to complete those tasks. Include remarks to recommend the ACL. Copy and paste the command onto the device. Always thoroughly test an ACL to ensure that it correctly applies the desired policy. This recommendation enables you to create the ACL truthfully without impacting the traffic on the network. Number standard IPv4 ACL syntax. To create a number standard ACL, use the following global configuration command: router config access list number deny permits per remark test short wildcard log. Use the no access list number global configuration command to remove it. The table provides a detailed explanation of the syntax for a standard ACL. name standard IPv4 ACL syntax. To create a name standard ACL, use the following global configuration command: router config IP access list standard access list name. This command enter the name standard configuration mode when you configure the ACL ACEs. ACL names are alphanumeric, case sensitive, and must be unique. Capitalizing ACL names is not required but make them stand out when viewing the running config output. This also makes it less likely that you will accidentally create two different ACLs with the same name but with different use of capitalization. Name standard IPv4 ACL syntax continue. It is example a name standard IPv4 ACL called no access is created. Notice that the prompt change to name standard ACL configuration mode ACE statement are entered in the name standard ACL subs configuration mode. You have facility to view all the name standard ACL ACE options. The three highlight options are configured like the numbers standard ACL. Unlike the numbers ACL method, there is no need to repeat the until IP access list command for its ACE. Numbers is standard IPv4 ACL syntax. The standard ACL is first configured and then it is activated on an interface. To create a number standard ACL, use the following global configure command. Use the no access list number global configuration command to remove an extended ACL. The command to apply an extended IPv4 ACL to an interface is the same for standard IPv4 ACLs. To remove an ACL from an interface, first enter the no IP access group interface configuration command. To remove the ACL from the router, use the no access list global configuration command. Protocol and port number. The standard ACL can filter on many different types of Internet protocol and port. Protocol option. The four highlighted protocol are the most popular option. Protocol ports keyword option. Selecting a protocol influences port option. For instance, selecting the TCP protocol would provide TCP relay port option. UDP protocol would provide UDP specific port option. ICMP protocol would provide ICMP related port option. The highlighted port are popular option. Port name or number can be specific, but port name make it easier to understand the purpose of an ACE. Protocol and port number configuration example. The standard ACLs can filter on different port number and port name option. This example configures an standard ACL 100 to filter HTTP traffic. The first ACE uses the www port name. The second ACE uses the port number 80. Both ACEs achieve the same result. Configuring the port number is required when there is not a specific protocol name list such as SSH or an HTTPS as shown in the next example. TCP establishes standard ACL. TCP can also perform basic stateful firewall serving using the TCP established keyword, thus enable inside traffic to exit the inside private network and permit the returning reply traffic to enter the inside private network. TCP traffic generated by an outside host and attempting to communicate with an inside host is denied. The established keyword can be used to permit only the return HTTP traffic from required website while denying all other traffic. The topology shows ACL 110 that will filter traffic from the inside private network. ACL 120 using the established keyword will filter traffic coming into the inside private network from the public. TCP established standard ACL. Continue. ACL 120 is configured to only permit returning web traffic to the inside host and then apply outbound the R1G0 interface. The show access list command display both ACL, the mask static so that inside hosts have been accessing the secure web result from the internet. The established parameter allow only respond to traffic that originate from the 192.168.10.0/24 network to return to that network. A must occur if the returning TCP segment has the ACK or reset flag bits set. Without the established parameter in the ACL statement, all traffic will be permitted. Name access extended IPv4 ACL syntax. To create a name extended ACL, use the following global configuration command. W. This command enter the name extended configuration mode. Recall that ACL names are alphanumeric, case sensitive, and must be unique. In the example, a name extended ACL called no FTP access is created, and the prompt change to name extended ACL configuration mode. ACE statements are entered in the name extended ACL sub-configuration mode. Name extended IPv4 ACL example. Name extended ACL are created in essentially the same way that name standard ACL are created. The topology demonstrates configuring and applying to name extended IPv4 ACLs to an interface. Surfing. This will commit inside HTTP and HTTP as traffic to exit to the internet. Browsing. This will only permit returning web traffic to inside host while all other traffic exiting the R1G0 interface is implicitly denied. The surfing ACL permits HTTP and HTTPS traffic from inside user to exit the G0/0/1 interface connected to the internet. Web traffic returning from the internet is permitted back into the inside private network by the Browsing ACL. Surfing ACL is applied inbound and browsing ACL applied outbound on the R1 G0/0/0 interface. Inside hosts have been accessing the secure web result from the internet. The show access list command is used to verify the ACL static. The permit secure HTTPS counter in the surfing ACL and the return established counter in the browsing ACL have increased name standard IPv4 ACL syntax. Two methods to modify an ACL. After an ACL is configured, it may need to be modified. ACL with multiple ACEs can be complex to configure. Sometimes the configured ACE do not yield an expected behavior. For the reason, ACL may initially require a bit of trial and error to achieve the desired filtering result. This section will discuss two methods to use when modifying an ACL. Use a text editor, use a sequence number. Text editor methods. ACLs with multiple ACEs should be created in a text editor. This allows you to plan the required ACEs, create the ACL, and then paste it into the router interface. It also simplifies the task to edit and fix an ACL. For example, assume ACL1 was entered incorrectly using 19 instead of 192 for the first octet as shown in the running configuration down below. The first ACE should have been 39. The host at 192.168.10.10, but it got incorrectly entered. To correct the error, copy the ACL from the running configuration and paste it into the text editor. Make the necessary change. Remove the previously configured ACL on the router, otherwise pasting the editor ACL command will only append to the existing ACL ACEs on the router. Assume that ACL1 has now been corrected. The incorrected ACL must be deleted, and the corrected ACL1 statement must be pasted in global configuration mode as shown in the output below. Sequence number method. An ACL ACE can also be deleted or add using the ACL sequence number. Sequence number are automatically assigned when an ACE is entered. These numbers are listed in the show access list command. The source running config command does not display sequence number. In the previous example, the incorrect ACE and ACL1 is using sequence number yet 10 as shown in the example down below. Use the IP access list standard command to edit an ACL statement cannot be overwriting using the same sequence number as an existing statement. Therefore, the current statement must be deleted first in the node 10 command. When the correct ACE can be added using sequence number 10 is configured. Verify the change using the show access list command as shown in the example down below. Now is my partner presentation.
Em tên là Hồ Thị Gia Bảo, mã số sinh viên 22IT.EB004, lớp 22ITE. Xin được thuyết trình về bài ACL. Today I'll be talking about implement ACLs. ACL configuration guidelines. An ACL is made up of one or more ACEs or statements. When configuring and applying an ACL, be aware of the guidelines summarized in this list. First, create an ACL globally and then apply it. Ensure the last statement is an implicit deny any or deny IP any. Statement orders is important because ACLs are processed top-down. As soon as a statement is matched, the ACL is exited. Always filter from the most specific to the most generic. Only one ACL is allowed per interface, per protocol, and per direction. New statements for an existing ACL are added to the bottom of the ACL by default. Router-generated packets are not filtered by outbound ACLs. Place standard ACLs as close to the destination as possible. Place extended ACLs as close to the sources as possible. So to apply an ACL, the command syntax to apply an ACL to an interface or to the VTY lines is router config if #IP access group ACL #name int out. Router config line #IP access class ACL #name in out. To remove an ACL from an interface, enter the no IP access group interface configuration command. The ACL will still be configured on the router, so use the no access list global configuration command to remove it. Name extended ACL example and named ACL on VTY lines with logins. Every ACL should be placed where it is the most efficient. Assume the objective is to prevent traffic that originates in the point 10 network from reaching the point 30 network. Extended ACL should be located as close as possible to the source of the traffic to be filtered. Undesirable traffic is denied close to the source network without crossing the network infrastructure. Standard ACL should be located as close to the destination as possible. If it was placed at the source of the traffic, the permit or deny will occur based on the given source address, no matter where the traffic is destined. Where to play ACLs can't. So placement of the ACLs and therefore the type of ACL used may also depend on a variety of factors as listed in the table. Standard ACLs should be located as close to the destination as possible. In the figure, the administrator wants to prevent traffic originating in the point 10 network from reaching the point 30 network. Choose possible interfaces on R3 to apply the standard ACL. R3 S0/1/1 interface inbound. If applied this way to deny traffic from the point 10 network, it will also filter the point 10 traffic to the point 31 network. The standard ACL should not be applied to this interface. So the G0/0/0 interface outbound, if applied this way, it will not affect other networks that are reachable by R3. So packets from point 10 network will still be able to reach the point 31 network. This is the best interface to place the standard ACL. So next is packet tracer. In this packet tracer, you will complete the following objectives. Part 1 is to configure and apply a name standard ACL, and part 2 is to verify the ACL implementation. The senior network administrator has asked you to create a name standard ACL to prevent access to a file server. All clients from one network and one specific workstation from a different network should be denied access. In this packet tracer, you will complete the following objectives. Part 1, plan an ACL implementation. Part 2, configure, apply, and verify a standard ACL. Well, standard access control list or router configuration scripts that control whether a router permits or deny packets based on the source address. This activity focuses on defining filtering criteria for configuring standard ACLs, applying ACLs to router interfaces, and verifying and testing the ACL implementation. The routers are already configured. So, extended ACL placement example. Well, extended ACL should be located as close to the source as possible, but the organization can only place ACLs on device that they control. In the figure, for example, Company A wants to deny Telnet and FTP traffic to Companies B, point 30 network from their point 11 network while permitting all the traffic. Two possible interfaces on R1 to apply the extended ACL. R1 interface outbound, it will process all packets leaving R1 included packets from the point 10 network. The interface inbound, only packets from the point 11 network are subject to ACL processing on R1 because the filter is to be limited to only those packets leaving the point 11 network. Applying the extended ACL to G0/0/1 is the best solution. So in this scenario 1, part 1, we configured, apply, and verify an extended numbered IPv4 ACL, and part 2 is to configure, apply, and verify an extended named IPv4 ACL. As in the scenario 2, we configure a named extended IPv4 ACL, apply and verify the extended IPv4 ACL. So next part is mitigate attacks with ACL. Well, mitigate spoofing attacks. ACLs can be used to mitigate many network threats such as IP address spoofing and denial of service DOS attacks. Most DOS attacks use some types of spoofing. In IP address, spoofing overrides the normal packet creation process by inserting a custom IP header with a different source IP address. Attackers can hide their identity by spoofing their source IP address. There are many well-known classes of IP addresses that should never be seen as source IP addresses for traffic entering an organization's network. Well, the S0/0/0 interface is attached to the internet and should never accept inbound packets from all zero addresses, broadcast addresses, reserved private addresses, RFC 1918, and 224.0.0.0.0/4. The network is attached to the R1 G0/0 interface that should only allow inbound packets with a source address from that network. The ACL for G0/0 shown in the figure will only permit inbound packets from the point 1 network. All others will be discarded. So permit necessary traffic through firewall. An effective strategy for mitigating attacks is to explicitly permit only certain types of traffic to a firewall. DNS, SMTP, and FTP, or services that often must be allowed through a firewall. Configure a firewall so that it permits administrators remote access through the firewall. SSH, syslog, and SNMP are examples of services that a router may need to include. While many of these services are useful, they should be controlled and monitored. Exploitation of these services leads to security vulnerabilities. An example topology with ACL configuration to permit specific services on the serial 0/0/0 interface is shown. Both ICMP, echo, and redirect messages should be blocked inbound by the routers. Several ICMP messages should be allowed into the internal network. First is echo reply, allows users to ping external host. Source quench requests that the sender decrease the traffic rate of messages. Unreachable, generated for packets that are administratively denied by an ACL. Several ICMP messages should be allowed to exit the network. Echo is allow users to ping external host. Parameter problem is to inform the host of packet header problems. If the packet is too big, enables packet maximum transmission unit MTU discovery. And lastly, source quench throttles down traffic when necessary. As a rule, block all other ICMP message types outbound. ACLs are used to block IP address spoofing, selectively permit specific services through a firewall, and to allow only required ICMP messages. The figure shows sample topology and possible ACL configuration to permit specific ICMP services on the G0/0 and S0/0/0 interfaces. Management protocols are useful for remote monitoring and management of network devices, but they can still be exploited. If SNMP is necessary, exploitation of vulnerabilities can be mitigated by applying interfaces ACL to filter SNMP packets from non-authorized system. An exploit is still possible, but if the packet is sourced from an address that has been spoofed and is permitted by the ACL, the most effective means of exploitation prevention is to disable the SNMP server on iOS devices for which it is not required. Use router config hashtag no SNMP server to disable SNMP services on Cisco iOS devices. In this packet tracer, you will complete the following objectives. Verify connectivity among devices before ACL configuration. Use ACL to ensure remote access to the routers is available only from the management station PC. Configure ACLs on R1, R2, and R3 to mitigate attacks. Modify ACLs and verify functionality. And that's it. Thank you for listening.
Hello, my name is Hodak Manyak. Today, I talk about IPv6 ACLs. IPv4 will coexist with IPv6 and then gradually be replaced by IPv6. An example of a security concern is threat actors leveraging IPv4 to exploit IPv6 in dual-stack environments. In a dual-stack environment, devices operate with two IP protocol stacks. Threat actor can accomplish steal attacks that result in trust exploitation by using dual-stack hosts, global NTP message, and tunneling techniques. Pseudo tunneling, for example, is an IPv6 transition technology that provides automatic IPv6 threat assignment when IPv4 IPv6 hosts are located behind IPv4 NAT device. It accomplishes this by embedding the IPv6 packets inside IPv4 UDP packets. The threat actor gains a foothold in the IPv4 network. The compromised host sends a rogue RAs, which triggers dual-stack hosts to obtain an IPv6 address. The threat actor can then use this foothold to move around or pivot inside the network. The threat actor can compromise additional hosts before sending traffic back out of the network, as shown in the figure. It is necessary to develop and implement a strategy to mitigate attacks against IPv6 infrastructures and protocols. This mitigation strategy should include filtering at the edge using various techniques such as IPv6 ACLs. All IPv6 ACLs must be configured with a name and allows filtering based on source and destination address that are traveling bound and about to a specific interface. They also support traffic filtering based on IPv6 option, header, and optional upper-layer protocol type information for finer granularity of control, like standard ACLs in by IPv4. To configure an IPv6 ACL, use the IPv6 access list command into IPv6 ACL configuration mode, and use the syntax shown in the figure to configure each AC to specifically permit or deny traffic. The syntax shown is a simplified version of the IPv6 AC syntax, but there are additional options. Apply an IPv6 ACL to an interface with the IPv6 traffic filter command. This is a table about IPv6 ACL syntax. An IPv6 ACL contains an implicit deny IPv6 NNE. Each IPv6 ACL also contains implicit permit rules to enable IPv6 neighbor discovery. The IPv6 NTP requires to use of the IPv6 network layer to send NAs and NS. If an administrator configures the deny IPv6 any command without explicitly permitting neighbor discovery, then the NTP will be disabled. In the future, R1 is permitting inbound traffic on G0/0 from the 2000 uh, colon TB8 colon 1 colon 1 colon colon slash 64 network. NA and NC packets are explicitly permitted. Traffic sourced from any other IPv6 address is explicitly denied. If the administrator only figured the first permit statement, the ACL could have the same effect. In the packet tracer, you will complete the following objectives: config, apply, and verify an IPv6 ACL. Config, apply, and verify a second IPv6 ACL. Access control list summary. An ACL uses a sequential list of permits or denied statements known as ACs. Packet filtering can occur at layer 3 or layer 4, and Cisco routers support standard and extended ACLs. Standard ACLs number 1 to 99 or 1300 to 1999, while extended ACLs number 100 to 199 or 2000 to 2699. MICLs are the preferred method to use when configuring ACLs. ACLs define the set of roles that give address control of packets that enter bound interface, packets that relay through the router, and packets that exist about interface of the router. An IPv4 AC uses a 32-bit wildcard mask to determine which bits of the address to examine for a match. A wildcard mask is like a subnet mask in that it uses the ending process to identify which bits in IPv4 address to match. Unlike to subnet masks, in which binary 1 is equal to a match and binary 0 is not a match. In a wildcard mask, the reverse is true. One shortcut method is to calculate wildcard masks is to subtract to the subnet mask from 255.255.255.255. SQL IOS provides two keywords, host and any, to simplify to most the most common use of wildcard masking. When configuring a complex ACL, it is suggested that you use a text editor and copy and paste the commands into the device. ACL names are alphanumeric, case sensitive, and must be unique. The procedural steps for configuring extended ACLs are the same as for standard ACLs. Extended ACLs can filter on many different types of Internet protocols and ports. TCP can also perform basic stateful firewall service using the TCP established keyword. ACLs with multiple ACs should be created in the text editor to make editing the ACL simpler. An ACL AC can also be deleted or added using the ACL sequence numbers. Sequence numbers are automatically assigned when an AC enters. Extended ACL should be located as close as possible to the source of the traffic to be filtered. Standard ACL should be located as close to the destination as possible. ACL can be used to mitigate many network threats such as IP address spoofing and DDoS attacks. An effective strategy for mitigating access is to explicitly permit only certain types of traffic through a firewall. To mitigate attacks against IPv6 infrastructures and protocols, the strategy should include filtering using techniques such as IPv6 ACLs. The ACL functionality in IPv6 is like ICL in IPv4, but there is no equivalent to IPv4 standard ACLs. In addition, all IPv6 ACLs must be configured with a name. IPv6 ACLs allow filtering based on source and destination address that are traveling bound and upbound to the specific interface. They also support traffic filtering based on IPv6 option headers and optional upper layer protocol type information for finer granularity of control, like standard ACLs in IPv4. New terms and commands. Asset control list ACL, wildcard mask, IPv4 ACL, IPv6 ACL, asset control entry ACA, number ACL, name ACL, standards ACL, standard ACL, IP access list, no IP access list, IP access group, IP access class, no IP access group, access list, no access list, TCP established keyword, spoofing attack, no SNMP server, IPv6 access list, IPv6 traffic filter, deny IP any, deny IPv6 any, so access list, inbound, outbound, any host, wildcard mask, keywords. Thank you for listening.